Deep in the ocean, a massive section of the Earth's crust snaps. In an instant, a column of water miles wide is heaved upwards, creating a pulse of energy that races across the sea at the speed of a jetliner. In the open ocean, this wave, a tsunami, might be less than a meter high, a subtle ripple on the surface. But as it nears a coastline, that subtle ripple transforms into a catastrophic wall of water. For most of human history, this silent, speeding threat arrived with little to no warning. Today, however, we have sentinels in space, watching over the oceans. They are part of a revolutionary science called Tsunami Tomography, which allows us to perform a CT scan on a tsunami from orbit, mapping its birth, predicting its path, and giving us a fighting chance against one of nature's most destructive forces. The core challenge with tsunamis has always been a race against time across immense distances. The 2004 Indian Ocean tsunami, which tragically claimed over 227,000 lives, was a brutal wake-up call. At the time, our primary system relied on seismic sensors. These sensors are excellent at detecting the underwater earthquakes that can cause tsunamis, but they have a critical blind spot. They can't tell you if a wave was actually generated. They can't measure its size or its direction. This uncertainty leads to a terrible dilemma for warning centers. Issue a warning and risk a massive false alarm, or wait for more information and risk being too late. A major upgrade came with the global network of DART buoys, which stands for Deep Ocean Assessment and Reporting of Tsunamis. These buoys have pressure recorders on the seafloor that can directly detect the change in water pressure as a tsunami passes overhead. They provide real-time, ground-truth confirmation that a wave is on its way. DART buoys are the cornerstone of modern warning systems, but the ocean is vast. They are still just a limited number of data points in an enormous space, and keeping them operational in the harsh ocean environment is a constant, expensive challenge. We needed a better view. We needed to see the whole picture. The idea of using satellites to spot tsunamis was once thought to be pure science fiction. The odds of a satellite with the right instruments flying over the right patch of ocean at the exact right moment seemed impossibly small, until it happened. On December 26, 2004, in an incredible stroke of scientific luck, two different satellites, Jason-1 and Topex Poseidon, passed over the Indian Ocean just 2 hours after the catastrophic Sumatra-Andaman earthquake. Their radar altimeters, originally designed to map the sea surface for climate science, captured the first-ever detailed portrait of a mega tsunami moving across the open ocean. The data was breathtaking. The satellites measured a clear anomaly on the sea surface, a leading wave with a crest up to 50 centimeters, or about 1.6 feet high, followed by a trough 40 centimeters, or 1.3 feet deep. To us, that might not sound like much, but to scientists, this was the unmistakable signature of the monstrous wave. And because two independent satellites measured the same thing, the data was irrefutable. For the very first time, we had a basin-wide snapshot of a tsunami in action. This wasn't the absolute first time a satellite had seen a tsunami. The Topex satellite detected a tiny 8-centimeter signal from a wave in 1992, but the 2004 event was on a completely different scale. It provided unambiguous, large-scale proof that satellites could be our eyes in the sky, and it kickstarted the field of tsunami tomography. So what exactly is tsunami tomography? The name itself gives us a clue. It comes from the Greek words tomos, meaning slice, and graphene, meaning to write. It's the same principle behind a medical CT scan, where doctors use multiple X-ray images, or slices, taken from different angles, to build a 3D model of your insides. Tsunami tomography does the same thing for the ocean. It's a 4-step process. First is detection from above. A satellite with a radar altimeter sends a pulse of energy down to the ocean, and measures the precise time it takes to bounce back. This gives an incredibly accurate measurement of the sea surface height directly beneath the satellite. A passing tsunami shows up as a clear rise or fall in that height. Second, you gather multiple slices. A single satellite pass is just one line of data. To build a full picture, scientists combine data from multiple satellite passes that cross the tsunami at different times and angles. They also integrate data from our existing dart buoys on the seafloor and coastal tide gauges. The more slices you have, the clearer the picture becomes. Third, and this is the really clever part, is the inversion. Using all these scattered measurements of sea level, powerful computer models work backward in time. They invert the data to reconstruct the very beginning of the event, the initial, massive uplift of the seafloor that gave birth to the wave. For example, using the satellite and tide gauge data from the 2004 tsunami, researchers were able to calculate that the earthquake's rupture was a mind-boggling 900 to 1, 400 kilometers long, with the seafloor being thrust upwards by as much as 25 meters in some places. This is a level of detail that would have been impossible to get without the view from space. And that leads to the fourth and most important step, forecasting the future. Once you have an accurate model of the tsunami's source, its initial energy and direction, you can run forecast models forward in time. This allows you to predict the tsunami's path, its arrival time at distant shores, and its potential height, with far greater accuracy than ever before. This was demonstrated again during the 2011 Tohoku tsunami in Japan. While Japan's world-class ground sensor network gave immediate alerts, satellite data was invaluable in the aftermath, providing rapid, wide-area assessments of the flooding. Satellite estimates of the wave's run-up height, like one of 39 meters at Rikuzen-Takata, were later validated by ground crews who measured an almost identical 39.7 meters. The 2004 event proved the concept, but traditional satellite altimetry has a weakness for real-time warnings. The satellites only see a narrow path, and the data can take hours to process. That's too slow to save lives at the start of an event. This has pushed scientists to develop new, faster, and more comprehensive technologies. The first major leap is a technology called GNSS-Reflectometry, or GNSSR. Instead of having its own powerful radar, a GNSSR satellite is more like a listener. It uses the signals that are already blanketing the Earth from navigation satellites like GPS, Galileo, and GLONASS. It passively measures how these signals reflect off the ocean's surface. The key advantage here is coverage. A traditional altimeter sees one point. A GNSSR receiver can see reflections from many navigation satellites at once, creating a wide footprint of observation points. This massively increases the probability of detecting a tsunami quickly. Studies show that a constellation of just 18 of these satellites could detect a strong tsunami within 15 minutes. A larger group of 48 satellites could catch even medium-sized tsunamis in under half an hour. This brings the detection time into the realm of actionable early warnings. And it gets even more interesting. Scientists found that tsunamis don't just change the ocean's height, they also change its texture. The turbulent front of a deep ocean tsunami creates a shadow of rougher water that can also be detected by satellite radars, giving another clue to the wave's presence. Then there's SWOT, the Surface Water and Ocean Topography satellite launched in late 2022. SWOT is a game changer. It uses a revolutionary instrument called a Ka-band radar interferometer. Think of it like this. Instead of a single radar beam, it has two, mounted on a 10-meter boom. This allows it to scan the ocean's surface in a wide, continuous swath, like a paintbrush stroking the sea. SWOT recently had its own breakthrough moment when it captured data from a tsunami generated by a massive earthquake off Russia's Kamchatka Peninsula. Just 70 minutes after the quake, the satellite provided a detailed 2D map of the wave, its height, its shape, its direction, with unprecedented precision. Vasily Titov, the chief scientist at NOAA's Center for Tsunami Research, said the results suggest that SWOT data could significantly enhance operational tsunami forecasts, a goal they've been working toward since the 2004 Sumatra event. SWOT is moving the science from just observing a line on the ocean to truly dissecting the entire wave in multiple dimensions. So where is this all headed? The future of tsunami defense isn't about one technology replacing another. It's about creating a seamless, integrated global shield. Satellites won't replace dart buoys or seismic networks. They are adding a critical, all-seeing layer on top. Let's imagine a future scenario. A powerful earthquake strikes a remote part of the Pacific Ocean. Within minutes, the global seismic network confirms its location and magnitude. Almost simultaneously, a constellation of GNSS-R satellites orbiting overhead begins detecting subtle but widespread changes in both the sea surface height and its roughness. This data is streamed instantly to warning centers like the National Tsunami Warning Center in the United States and the CENALT Center in France. An automated system immediately performs a rapid tomographic inversion, using the flood of satellite data to build a precise model of the seafloor rupture and the initial energy of the wave. This allows forecasters to confirm not only that a tsunami was generated, but exactly how powerful it is. A short time later, a high-resolution satellite like SWOT passes over, providing a detailed 2D map of the propagating wave, which is used to fine-tune the forecast models even further. With this stream of high-confidence information, warning centers can issue incredibly accurate and targeted alerts, telling specific coastal communities exactly when the wave will arrive and how big it will be, giving them the precious time they need to evacuate. From a single, lucky observation in 2004 to a dedicated global network of sophisticated space-based sentinels, the science of tsunami tomography has evolved at an incredible pace. By giving us the power to see, measure, and understand these immense ocean waves from their very birth, satellites are fundamentally changing our ability to defend against their devastating impact. They provide the ultimate high ground, the perfect vantage point from which we can watch over the world's oceans, turning a terrifying unseen threat into a calculated and increasingly manageable risk.